Hello dear students and welcome to part 5. We are on to question number 3 and each sub-question in question number 3 carries a weightage of 5 marks. Let's get started with problem A. It is from the module matrices. We are given find ABC if the matrix A is 1/3 of this and it is orthogonal, and then we are also required to find A inverse. Now we are provided the data that the given matrix is an orthogonal matrix. So based on that, firstly we are going to determine the constants A, B and C, and once we have determined the constants A, B and C, we will go ahead and find A inverse as well. Now to start with, we'll take the help of orthogonality of a matrix. So we know that since A is orthogonal, this implies that A times its transpose is going to be the identity matrix order 3. So therefore A is 1/3 of this times A transpose will be, the rows will be swapped with the columns, so we get this matrix. Must be equal to the identity matrix of order 3 by 3. Now as you can see that on the right side only the diagonals are significant, all non-diagonal entries are 0. So when we take the product of these two matrices, we will be only interested in the diagonal entries. So therefore we will be getting the first diagonal entry to be 1 by 9, and that is going to come from the first row multiplied by the first column. So that is going to give us 1 into 1 plus 2 into 2 plus 3a into 3a, and that will correspond to 1 on the right side. Likewise, the second diagonal entry on the left is going to be 1 by 9 times 2 into 2 plus negative 1 into 1 plus 3b into 3b. This will correspond to 1. And the third diagonal entry on the left will be 1 by 9 is equal to 2 into 2 plus 2 into 2 plus 3c into 3c is equal to 1. From the expression over here, we will be getting 5 plus 9a square is equal to 9. From here, we will be again getting 5 plus 9b square is equal to 9. And from the third one, we will be getting 8 plus 9c square is equal to 9. Now, since we are interested in the values of the constants a, b and c, let's isolate a, b and c. So we have got here 9a square is equal to 4, which is going to give us a as plus minus 2 over 3. Similarly here, we will be getting 9b square is equal to 4, which is going to give us b is equal to plus minus 2 over 3. And here 9c square is equal to 1, which will give us c is equal to plus minus 1 over 3. So thus we have got the values of a, b and c. That was the first part which was required as our solution. Now moving on to the second part, we also need to find out a inverse. Again, for this we are going to use the orthogonality of a. Since a is orthogonal, this implies that the inverse of A is nothing but its transpose. So we'll just write down the transpose of A, and we are going to incorporate the values of A, B and C that we have just obtained. So this is going to be 1 over 3, and then we will have the first row to be 1, 2, 2, the second row to be 2, 1, negative 2. And now in the third row we are going to have 3A. So when you take the product of A and 3, you are going to get plus minus 2, B again plus minus 2, and this is going to be plus minus 1. So that is question number 3A. Now let's quickly move on to question number 3B. So this is question number 3B. It is from the module complex numbers, hyperbolic functions, and logarithm of a complex number. So we are given that alpha and beta are roots of this quadratic equation, and we want to prove this relation between the roots alpha and beta. It's a cubic relation. So to begin with, we'll first determine what alpha and beta are going to be. So we are going to use the quadratic formula. So we can say that here A is 1, B is -2 root 3, and C is 4. So therefore, by using the quadratic formula, which is -b plus minus square root of b square minus 4ac over 2a. So this is going to be, so negative of b will become 2 root 3 plus minus square root of b square is going to be 12 minus 4 into a into c, that's 4 into 1 into 4, which is 16, divided by 2 times of a, and that is going to be 2. So this is 2 root 3 plus minus, we'll get square root of -4, that will be 2i over 2. So that is root of 3 plus minus I. So since there are two roots and the two roots are denoted as alpha and beta, so let us say alpha is equal to square root of 3 plus I, and beta, now since the roots are in pair, the two roots are going to be complex conjugate. So we can say that beta, which is alpha bar, is equal to square root of 3 minus 1. Now we are going to take help of complex numbers. In particular, we are going to use the polar form, and which will be followed by de Moivre's theorem. So for alpha equal to root of 3 plus I, we will find out the modulus of alpha, that is denoted by r, and it is given as square root of 3 square plus 1 square, everything inside the square root. That comes from the formula r is equal to square root of x square plus y square. So that turns out to be 2. We'll also need theta. Theta is evaluated as tan inverse of y by x. So that's going to be 30 degrees or pi by 6. So we can say that alpha in its polar form is going to be 2 times of cos of pi by 6 plus I times sine of pi by 6. While beta, which is the complex conjugate, is going to be 2 times cos of pi by 6 minus I times sine of pi by 6. Now, if you will have a look at the expression which we are going to prove, we need the cubes of alpha and beta. So let us cube them. So alpha cube will be 2 cube into cos of pi by 6 plus I times sine of pi by 6 whole cube. Now, by the application of de Moivre's theorem, this is going to be cos of the power 3 gets multiplied with the argument. So we will get 3 pi by 6, which reduces to pi by 2 plus I times sine of pi by 2. And likewise for beta cube, we will be getting 8 into cos of pi by 2 minus I times sine of pi by 2. Now continuing with alpha cube, you see that you have got cos of pi by 2, which is a standard known value. So we can put the value of cos pi by 2, which is 0. So we will be only left out with 8i, and since sine of pi by 2 is 1, so we'll be left out with only 8i. And likewise over here, we will be left with negative 8i. So when we take the sum of alpha cube and beta cube, we will be getting 8i plus minus 8i, which is equal to 0, thus giving us the required proof. So that's question 3b. Now let's move on to question 3c. So this is question 3c. It is based on successive differentiation, and to be particular, it is based on Leibniz theorem. So we are given a function y, which is sine inverse of x, and then we are required to prove this expression. If you will notice, we have here the n plus 2th order derivative of y. then n plus 1th order derivative of y, and the nth order derivative of y. So these things come after successively differentiating y n times or more than that. So to begin with, we will start with y. So we are given that y is equal to sine inverse of x, and differentiating it, we are going to get y1, which is going to be square root of, which is going to be 1 over square root of 1 minus x squared. And cross multiplying and taking the squares on both the sides, we will be getting 1 minus x square into y1 square is equal to 1. Let us call this as equation number 1. Further, we are going to differentiate it one more time. So differentiating again. So now since it is product of two terms, so we are going to take help of the product rule, also commonly known as the UV rule. So that's going to be u as it is multiplied by the derivative of v. The v part over here is y1 square. So that is going to be 2y1 into y2. So the other y2 comes as an application of chain rule, because we got to differentiate y1 again, and differentiating y1 is going to give us y2. Then plus derivative of u, so that is going to be minus 2x into v as it is, and on the right hand side it is going to give us 0. So on simplifying, you can see that 2 could be factored out and it will get cancelled. So we will be having 1 minus x squared y1 y2 minus x into y1 square is equal to 0. Also we can factor out y1, so we can say that y1 into 1 minus x square y2 minus x into y1 is equal to 0. Now since we have on the left side we have product of two expressions and it is equal to 0, then we can try and figure out whether one of them is 0. So that could be done by taking help of this expression. Now have a look at y1. Now since y1 is a rational function and the numerator is constant 1, which is a non-zero number, so for any value of x, this y1 is never going to become 0. So we know that y1 cannot be 0. So therefore the other factor has to be 0, which means that 1 minus x square times y2 minus x times y1 is equal to 0. And here we could give the reason that y1 cannot be equal to 0. Now once we have this, we will differentiate it n times now. Now why do we differentiate it here is because have a look at the problem. You are required n plus 2th order derivative. So the n plus 2th order derivative will come after you differentiate y2 n times. So since we have got y2, now we come at the stage wherein we are going to apply the Leibniz rule and differentiate this expression n times. Let me write down Leibniz theorem in short. So the Leibniz theorem, it is applicable for finding the nth order derivative of a product uv, and it is given as sigma k from 0 to n. Then we have got n c k into u n minus k into vk. So if we'll plug in the initial values of k, we are going to get un into v0 plus n un minus 1 into v1 plus n minus 1 over 2 into un minus 2 into v2 and so on. It's a finite term, it has an end, but right now we are not interested in that. So we will be taking the nth order derivative. Now since you have got a sum in the last expression, we are going to apply the Leibniz theorem for this as well as this separately. So differentiating n times, we will be getting 1 minus x square y2, the nth order derivative of this expression, and over here the nth order derivative of x times y1 is equal to 0. So we'll be first talking about the first term. So let's first talk about the nth order derivative of 1 minus x square into y2. Now over here we need to make a choice of u and v. We always choose the variable v, the function v, as to whose derivative is going to vanish faster. So over here we can see that we have a polynomial 1 minus x square, and this derivative is going to become 0 faster. So we are going to say that u is equal to y2 and v is equal to 1 minus x square. So we have got v0, which is 1 minus x square. Then we will need v1, which is negative 2x. v2 is equal to negative 2, and v3 onwards, all other higher order derivatives of v are going to be 0. Now, along with v0, you need un. Along with v1, you need un minus 1. And along with v2, you need un minus 2. So let us write down. So un is going to be the nth order derivative of y2, and that's going to be a straightforward yn plus 2. Then we need un minus 1. So since one derivative order is lesser, this is going to be yn plus 1. We need un minus 2, that is going to be yn. And after this, we do not need the other derivatives since these terms are all going to cancel out each other. So therefore, the expression over here is going to be, so we need un into v0, that's going to be yn plus 2 into 1 minus x square plus n times yn plus 1 into minus 2x plus n into n minus 1 over 2 into yn into negative 2. And after this, we will have all terms to be 0. So we can just simplify this. 1 minus x square yn plus 2 minus 2 nx yn plus 1. Then over here we will have minus 2 n into n minus 1 yn. So that's the nth order derivative of the first term. Now moving on to the second term. So we will be applying Leibniz rule to this expression directly. So for the nth order derivative of x y1, you can see that x is the one which we will be choosing for v. So we will be getting 1 into yn plus 1 into x plus n into yn into 1, and after this all other terms are going to be 0. So this simplifies to x yn plus 1 plus n times yn. Now we'll club in and put everything in this equation. So we will have from start 1 minus x square yn plus 2 minus 2nx yn plus 1. Over here the 2 factor is going to go away, so we don't need that. So we will just have minus n into n minus 1, and that can be simplified as n square yn plus nyn, and then the other terms come from over here. Please make a note that we have a negative sign here. So this is going to be minus x yn plus 1 minus n yn. On the right we got a 0. So as you can see, we can get rid of these two terms. So we are going to have 1 minus x square into yn plus 2. Now we have two yn plus 1 terms, so we can collect them. And you can see that x is a common factor as well. So we can rewrite this as minus 2n plus 1 x into yn plus 1 minus n square yn is equal to 0. This is what we were required to prove, and thus we are done. So with this we complete this video. I hope that you are following. If you have not yet subscribed to my channel, please do subscribe and also press the bell icon to get notified about the upcoming videos. Thank you so much for watching till here. Happy learning.